The Quincy Mine is one of Michigan's most historic sites, a copper mine that operated for nearly a century, producing 800 million tons of copper. Today, it's a National Historic Area, and we've spent the past 2 years studying whether it can provide its own clean energy. As you can see behind me, the mine has a 6.5 kilowatt array that was installed in 2016, but went offline in 2021 due to the cable being damaged. In our analysis, we strove to answer 2 questions. Is it worth it to repair this array? And what is the best configuration for a new array somewhere on the site? To answer those questions, we used PVlib, a Python package, and NREL's System Advisor model to model the energy production from this array and from prospective arrays at different locations up top. We used a typical meteorological year and snowfall data from the National Ocean and Atmospheric Administration in order to properly model the significant weather up here. The snow D rate turned out to be 11% annually, which matters a lot in northern climates. The 3 sites that we evaluated are here down by the adit entrance and 2 sites up top, on the gift shop roof and on a roof of a new pole barn that's yet to be built. Across the arrays, tilt, azimuth, and module type varied. We tested monofacial on the roofs and bifacial down here by the adit. We found that the bifacial configurations produced the highest specific yield.
For financials, we use net present value as our single evaluation metric. It utilizes energy production, price escalation, as well as installation costs all in one number. We got cost estimates from a local contractor and ran sensitivity analysis across discount rates of 3%, 5%, and 7%, as well as energy escalation rates at 2% and 5%. We tested 2 incentive scenarios, a 40% tax credit with no grant and a 22.5% ITC with a 25% grant. All 4 new array configurations showed positive NPV, with the 36 panel array being the strongest. We also evaluated simply repairing the current cable, which came in at an NPV of $14,000 and a payback period of 3.3 years, and can also be installed at the same time as the new array configuration. On the environmental side, we also led a GIS-based site analysis and life cycle assessment using OpenLCA. The site soils are type A with high infiltration rates and low disturbance rates, meaning that hydrologic impacts from installation will be relatively minimal. Both of the 24 panel configurations showed a carbon payback period of approximately 1.4 years, with the 36 panel configurations being about 1.5 years, which is pretty on par for carbon payback periods in the United States. The full engineering design for the best performing array will be completed in fall 2026 and will include a 1-line diagram, wire sizing calculation, as well as equipment specs. Our analysis clearly supports expansion. The Quincy mine has the solar energy, the resources, and the incentives to make this work.